Pre-calculus students, general seekers of truth in particular, we will now start and finish our proof for the explicit formula of the minimum number of moves needed to solve the Tower of Hanoi. So this is our claim that we're making. And now I'm going to take away the question mark here because we're actually going to attempt and prove this. So this is our claim that the explicit formula for the minimum number of moves required to solve the Tower of Hanoi with n disks satisfies the equation 2 to the n minus 1. That was quite wordy, so I suggest you try to unpack that for yourself in your mind, what I just said there, and make sure that it fully makes sense for you. The claim is the minimum number of moves to solve the Tower of Hanoi with n disks satisfies the equation 2 to the n minus 1. Okay. And well, how do we go about proving this sort of claim? So one of the things that we could do is we could try different values of n. And let me clarify one thing here. We are talking about n greater than or equal to 1. Okay, so for all n greater than or equal to 1, all of the counting numbers. So to prove that we can try different values of n. So let n equals 1. Then 2 to the 1 minus 1 is equal to 1, which matches our result here. Check, that works. How about n equals 2? 2 to the second minus 1 really does equal 2. So it really does equal 3. So check, that works for this step. And we could keep going on like this, on and on and on and on forever, but we don't actually have enough time to do this forever. So we need a better way to approach this problem. So this is how we're going to approach it. We are going to say a couple of things. That the claim, we're going to do this in two parts. In part one, we're going to say that the claim is true for n equals 1. And in the second part, and this is the trickier one, we can say that for any integer, k, for any, sorry, I should say positive integer, but be very specific here. For any positive integer, k, if the claim is true for k, it must also be true for k plus 1. Okay, so if the claim is true for k, it must also be true for k plus 1. And let's just think about what this is saying. We break this into two parts. The claim is true for n equals 1, and then for any positive integer k, if the claim is true for k, it is also true for k plus 1. And you can see that that sort of mimics the recursive part here. So we got the saying that the claim is true for 1 is really saying that a sub 1 equals 1. And saying that the claim is true for the second statement here, for any positive number k, if the claim is true for k, it is true for k plus 1. That just really means if it's true for the previous term, then it must also be true for the current term, in this case, the number of disks. Okay? So let's prove the two parts. And I should say one more thing. this statement here, if the claim is true for k, it is also true for k plus 1. This is basically saying assume true for k, and then we want to show that it is true for k plus 1. All right, so now let's get down to this business. So proof of the first part. What was the claim again? The claim was that a sub n is equal to 2 to the n minus 1. So when n is equal to 1, a sub 1 would be equal to 2 to the first minus 1, which is equal to exactly 1. So done. That's so simple to do. That's the easier part. Now here comes the trickier part. Prove that the claim is true, that if the claim is true for k, it must be true for k plus 1. So we can assume that a sub k is equal to 2 to the k minus 1, and we want to show that the claim is true for k plus 1. So show that a sub k plus 1 is equal to, and all we're doing here is substituting in k plus 1 for n. So show that a sub k plus 1 must be equal to 2 to the k plus 1. And so this is what we're going to do to prove it. We're going to use the recursive step here. So we know that a sub k plus 1 must be equal to, using the recursive definition, 2 times a sub k plus 1 by the recursive formula. For the Tower of Hanoi. Okay. I'll abbreviate this, TOH, for the Tower of Hanoi. But we can expand this and apply the explicit formula for a sub k. We can do that because that's our assumption. We're going to assume that this is true for a sub k. So this is a sub k is really equal to 2 to the k minus 1 and then plus 1. And so we're using this is called the recursive assumption. I'm sorry, it's not the recursive assumption, it's the inductive assumption. But I'm just going to write that it's true by our assumption here. Or this is called the inductive hypothesis. Sorry. Let's undo this here by the inductive hypothesis. So that's what this statement is right here. Assume that it's true for k. Show that it is true for k plus 1. So this is called the inductive hypothesis. All right, so that's by the inductive hypothesis. And now what's left for us to do here is just to work out a little bit of algebra. So 2 times 2 to the k, to distribute this is 2 times 2 to the k minus 1. No, it's minus 2. And then you have this plus 1 here. Now, let's just see. this 2 here is really 2 to the first, so this is really 2 to the first times 2 to the k. So this is going to give us 2 to the k plus 1. And then the negative 2 and positive 1 will just give us negative 1. And this formula matches this formula exactly, and so we are done proving the second step. So we know that the claim is true for the very basic case of n equals 1, and we know that if the claim is for all numbers k, if it's true for k, then it must be true for k plus 1. So this is another way of saying a sub k implies that that a sub k plus 1 is true. So if a sub k is true, it implies that a sub k plus 1 is true. So for all possible positive integers, if the claim is true for k, it must be also true for k plus 1. So then that means, in combined with step 1 here, the claim is true for all positive integers, starting from 1 and above. So herein we conclude our proof here, and this is the way that we approach a problem like the Tower of Hanoi, where we have a recursive process to this that's very straightforward to figure out. We have an explicit formula that we think is true, and we want to show that it's true for all n, for all possible number of disks. So what we do is we show that given, and this is the step 2 here is the key part, that given any value of k, if the statement is true for that number k, it must also be true for the next number. Therefore, it's true for all numbers. So this is kind of a domino effect. If the first domino falls and one domino knocks down the next domino, then all of the dominoes must have fallen. So that's basically how and this type of proof works. This is called a proof by induction, and we will define it a little bit better in greater detail in the next video. As always, thank you for watching, and have a wonderful